Hey guys, Jake here coming at you with another math lesson today. Today we're going to be talking a bit about rational functions as well as how to find the domain. More specifically, we're going to touch a little bit on vertical asymptotes within these rational functions. So like I've been kind of saying in my last few videos, trying to take a little bit more casual approach of just kind of going through some topics in a little bit more detail. Not worrying so much about the production and just trying to get good value out to you guys. So if you like the new format, do me a favor, hit that like button down below. Huge help to my channel so we can get these videos out to more people and start growing the Jake's Math Lessons community a little bit more. But let's go ahead and jump into rational functions. So first of all, what is a rational function? Well, a rational function is one that is always going to have this kind of general form here where we have it's kind of split into a fraction basically, where you have, your numerator of your fraction, your denominator of your fraction. You're going to have some, x's in both the top and the bottom of your fraction here, where each function, so the numerator function and the denominator function, are both polynomials. And on top of that, the denominator function is not the zero polynomial. So if the denominator function was the zero polynomial, we would have something like this, n of x over 0, which does not exist, right? Because you can't divide by 0. So that kind of topic is going to come up a little bit more throughout this video. You always want to keep that in mind in general. Dividing by 0 is basically breaking a rule of math. So if you're ever in a situation where you're dividing by 0, that should sound off some alarm bells in your head, right? So just make sure that's not the case. But as long as that's not the case, as long as you have a polynomial on the top, a polynomial on the bottom, that's a rational function, okay? So I've talked about polynomials a little bit over the last few videos I've made, but let's kind of take a sec to talk about what that means. So a polynomial is a function that is made up of the sum of a bunch of different terms that are a coefficient times x raised up to some positive whole number power. So you'll usually see it written like this: a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 plus a2x squared plus a1x plus a0. Okay, so this is a lot of different symbols, and a lot of people get really confused by this sort of notation, but just keep it in mind. Really, all it comes down to, all this is saying is the sum, so a bunch of different terms being added or subtracted, where each individual term is just some constant coefficient. So a sub n is just some number, right? Could be 1, could be 10, could be the square root of 2, it could be negative 16. It's just a number, right? So a sub n, these a sub somethings, these are just numbers. It's just any number. They just use a different subscript to show you that each coefficient could theoretically be a different number, okay? Times x raised up to some positive integer power, which just means a positive whole number. So it could be x to the first, which would be like this term right here. That's x to the first. It could be x squared. It could be x to the 10th, the 20th, the 100th, the millionth, but it can't be a negative number, and it has to be a whole number. So for example, 16x to the 3 halves, a term like this cannot be in a polynomial. That's not a whole number power. That's not a polynomial. If you have 16x to the negative 3, that's a negative number, right? That's not a positive whole number power. So this would not be a term within a polynomial. However, x to the 16x to the positive 3, that could be a term in a polynomial. So it just has to be a positive whole number power, okay? The coefficient doesn't just have to be a positive whole numbers, right? We could have negative 16x cubed. We could have the square root of 2x cubed. We could have negative 3 halves x cubed, right? These are all terms that could be in a polynomial as long as we have it, just some number times x raised up to a positive whole number power. So as long as you have a fraction function where the top and the bottom of that fraction are just a polynomial, that makes a rational function, okay? So that's all a rational function is. So let's talk about the domain of rational functions. Like I just said a moment ago, if you're ever in a situation where you're dividing by zero, that should sound off alarm bells in your head. You should never divide by zero, okay? So when you're looking for the domain of a rational function, the main thing you want to look out for, okay, there could be other things that well, actually no, because yeah, then they wouldn't be a rational function. I was going to say making sure you're not taking the square root of a negative, but that would not be an irrational function. So in general, there's kind of three main things you want to look out for when you're talking about the domain of any function in general. In that includes, you want to make sure you're not taking the square root of a negative number, you want to make sure you're not dividing by zero, and you want to make sure you're not taking the log or natural log of a negative number or zero. That's a little bit of a tangent, that's a little bit off topic. When it comes to rational functions specifically, which is what we're talking about in this video, you really just need to look out for the dividing by zero thing, okay? That's the main piece you want to keep in mind. So we're going to go ahead and go into an example here, and I'm going to tell you a little bit more detail about what I mean there. Before we do that though, do me a favor, go check out this link right here, jakesmathlessons.com/precalculus-study-guide. You can also scan this QR code in the upper right hand corner of your screen. It takes you to the same place. I just recently came out with my Precalculus study guide. I'm doing a little bit of a, kind of Precalculus circuit of videos where I'm going through all the topics on my channel that are covered in that study guide. That should be a huge, helpful resource for you as you study, as you do homework, as you prepare for tests, anything. If you're taking a Precalculus test, Precalculus class, you're definitely going to want to go check out that study guide. So go to that URL there. You can go get yourself a copy. It's available for instant download. So you can start using it today. You can print it out, save it as a PDF on your desktop, whatever, whatever you like to do, but it's going to save you time, I promise. So let's go ahead and go into this example. Let's find the domain of this function and identify any vertical asymptotes. So here's the function we have, f of x equals x cubed over x squared minus 1. So first of all, going back to what we were just talking about, is this a rational function? Well, let's think about what we have here. We have x raised up to some positive whole number power as our entire numerator. Okay, so x cubed, that's a polynomial. What about our denominator? X squared minus 1. We have x raised up to a whole number positive power, and then just plus or minus a constant term. So a constant term is okay, right? We could have x terms, we could have constant terms, which could be -1, could be 5, could be 10, could be square root of 2, whatever our constant term is, that's fine. As long as we have our positive whole number x's, positive whole number power x's, sorry. So x squared minus 1 is an example of a polynomial, okay? So this fraction, this function, is just a fraction where both the top and the bottom of that fraction are polynomials. So when we have a polynomial over a polynomial, we have a rational function. So this definitely is a rational function. Okay. So how do you find the domain of a rational function? Like I just kind of talked about a moment ago, when you're looking to find domains of functions, usually the way I like to think of it, the thing I like to think is easiest, start with all real numbers. Start with your domain being any possible x value we could plug into this function. Then what you want to think about is, what are some x values that actually we can't plug into this function because it'll break the rules of math somehow. And whenever you have a rational function, whenever you have a fraction in general, but you're always going to have a fraction when you have a rational function, the thing that your brain should go to is dividing by zero. You can't divide by zero. No matter what, you never should have 0 on the denominator of a fraction, because if you do, you're dividing by 0, and anything divided by 0 does not exist. Some people think that dividing by 0 gives you 0. That's not true. If you get 0 on the bottom of a fraction, you've broken the rules. You need to go back and do something different. So if we make sure that our denominator here does not equal 0, then we should be fine. There shouldn't be any other limitations here of x values that we can plug into this function, as long as we make sure we're not dividing by 0, right? There's not going to be logs, there's not going to be square roots in a rational function because then it's no longer a rational function. Then we just don't have, polynomials in our top and bottom of our fraction. So dividing by 0 is the main thing you want to look out for here. If those other two things, the square root of negatives, the log of negatives, or 0 is confusing you, forget about those. Those are not really relevant to rational functions at all. We will, come back to those at some point in the future. Don't worry about them. For now, just focus on the dividing by 0 part. And I know I've said that probably 1,000 times in this video, but I really just want to drill that point home. Dividing by 0 breaks the rules. You can't do it. So we need to make sure that whatever is in the denominator of our rational function does not equal 0. Well, how do we do that? Really, all you have to do is set the denominator equal to 0. So take whatever your denominator is, x squared minus 1 in this case, set it equal to 0, and figure out what x values cause this to happen. If we take this equation, setting it equal to 0, and solve for x, that's going to give us a list of numbers that we cannot plug into this function. So therefore, we can remove them from our domain, or from our list of all possible x values, and then we know whatever's left is within the domain of our function. It's okay to plug into the function. So how do we solve an equation like this? Usually when it comes to polynomials, that's just going to be a matter of finding the zeros of the polynomial. I've made a few videos recently about how to find the zeros of a polynomial. I'll come back and try to put an info card up there, so you can go click that if you want to check out that. But usually it's going to come down to factoring, right? There's some other methods we can use, kind of shortcuts for really complex polynomials. But if it can be factored, that's usually going to be the easiest way. So in this case, we have x squared minus 1. To factor this, we can actually just use the difference of squares. So difference of squares says if you ever have a squared minus b squared, you can factor that as a plus b times a minus b. So in other words, if you have a square number minus a square number, or a square term minus a square term, in this case, x squared is obviously a squared term. It's x squared. And then 1 is a square number. It's 1 squared. Right? So we could think of this as x squared minus 1 squared equals 0. And now this perfectly goes into our difference of squares formula, where we have x plus 1, x minus 1 equals 0. Okay? So once we've factored it, the reason why that's really nice is because when you have multiple factors being multiplied together, and you know that is supposed to equal 0, you can split it up into 2, or if you have more than 2 factors, you can split it up into multiple different, smaller, easier equations. Because if you take each one of these factors and set it to 0, the solutions to each of these equations is going to be a solution to this equation. Let's think about why that is. If either one of these factors equals 0, so if x plus 1 equals 0, or if x minus 1 equals 0, then the product of any number times 0 is also going to be 0. So as long as either one of these two things happens, this whole equation will equal 0, because 0 times any number is 0. Okay? So this gives us two much easier equations to solve. With this one, we can just subtract 1 from both sides, giving us x equals negative 1. With this one, we can just add 1 to both sides, giving us x equals positive 1. Okay? So x equals negative 1, x equals positive 1. Those are the two x values that would cause us to divide by 0 in our original function. Okay? So what that tells us is x equals 1 and x equals negative 1 need to be removed from our domain of our function. If we, think about having all real x values as our possible domain, we need to remove these two out because we cannot plug those into our function. If we do, we divide by 0 and we broke the rules of math. Okay? So that means that our domain is just going to be basically our domain. Let's actually do this in a different color here. So the domain of our function, so we started with all real numbers, right? We started with negative infinity to infinity. But we need to take out x equals negative 1 and x equals 1. So actually we're not going to use all these numbers here. We're going to have to remove some. So let's kind of erase part of this. We're going to start at negative infinity, but then we're only going to go up to our smallest x value that we have to remove, which is negative 1. So we're only going to go up to negative 1. Okay? Then we're going to go from that smallest x value to the next smallest x value, which in this case is 1. So we're going to go then from -1 to +1. And then we're going to go from that x value to the next smallest x value. Well, in this case, there are no other smaller x values. So we're just going to go all the way up to the rest of infinity from there. So basically, we're taking the domain of -infinity to infinity, pulling out the individual numbers we don't want, and that's giving us these kind of like little breaks in the number line, basically, the breaks in the domain. So any number from -infinity to -1, -1 to 1, 1 to infinity, which is basically all numbers except -1 and 1, which are the two numbers that are basically in between these little gaps between these different intervals. The reason why we've used these round parentheses as our edges for each of these intervals is because we don't want -1 or 1 to be included within our domain. So we use the round parenthesis to exclude those. So this is the domain of our function. So now we need to think about identifying any vertical asymptotes. Well, when you're talking about a rational function, basically these points where you can't plug in that x value because it causes you to divide by 0, these are going to be the places where you have vertical asymptotes. Okay? In general, if you have a fraction function like this, the places where dividing by 0, or the places where whatever x value you plug in will cause you to divide by 0, these are either going to be holes or vertical asymptotes, which we'll just abbreviate to VA. How you can kind of figure out which is which is basically by factoring out the whole numerator and the whole denominator. Okay, so we factored out the denominator and we figured out that our function f of x was equivalent to our function f of x in this case is equivalent to x cubed over x plus 1 times x minus 1. Okay. What we would want to do is factor out our numerator fully as well. In this case, x cubed is already fully factored out. There's really no factoring we can do there. Okay. So as a result, this is the fully factored out version of our original function f of x. Once you get it to that fully factored out point, you want to kind of think about if there's any terms on the top and the bottom of your fraction that cancel. In this case, there's nothing that's going to cancel, right? Let me give you an example of one that would. Let's say our function, let's say we factored it all out. We had some function g of x. We factored it all out to x squared times x minus 1 over x plus 1 times x minus 1, okay? So in this case, we get it all fully factored out, and we see that we have an x minus 1 in the numerator and the denominator, and these would cancel out, okay? What that tells us is that the x value that caused us to divide by 0 right here, so in other words, setting this factor equal to 0, x minus 1 equals 0, and getting x equals 1, this x value that caused this factor to be 0, since it canceled out, this would be a hole. So if the factor cancels with something in the numerator, that tells you that x value that caused you to get 0 from that factor would be a hole and not a vertical asymptote. The other factor that does not cancel, if it does not cancel, then the x value that caused that factor to equal 0, in this case x equals -1, this would be a vertical asymptote because it did not cancel. So in this case, going back to, I just wanted to give you an example of what it would look like for a hole versus a vertical asymptote. You may be at the point in your precalculus book or your precalculus course where you're not really talking about holes yet. So if you're at that point and this kind of threw in an extra wrinkle that's a little confusing, just ignore this. However, it may be coming. You may need to learn about this at some point. So I want to just kind of point out the difference of how to identify a vertical asymptote versus a hole. In the actual example we were doing here, right, this f of x equals x cubed over x squared minus 1, it factors out into this. there's no factors that cancel, right? So we don't even need to worry about, since there's no canceling, we don't need to worry about any holes. We know that both these x values, x equals -1 and +1, these are both going to be vertical asymptotes in this case because there's no canceling. So we actually have two vertical asymptotes, x equals -1 and x equals 1. And this is the correct way that you would write the form of a vertical asymptote. A vertical asymptote is always going to be a horizontal line equation, which is always going to be x equals a number. So these are your two vertical asymptotes. These are also the two x values that you need to exclude from your domain. And doing so leaves you with this as the final answer for your domain of this function. So that's it. Hope you got some value out of this video. If you did, do me a favor, hit that like button down below. And like I said, if you do want to go check out my Precalculus study guide, I think that is going to be a huge help to you. So go check out that URL right there. And I'll see you next time. Thanks.